Okay, this video is the beginning video to learn about Ksp. Okay, the Ksp stands for the solubility product constant. It's an equilibrium expression. It has to do when something is dissolving in water, or it can be dissolving in a solution, but for right now we'll just stick with dissolving in water. So the first thing that you need to know is that the larger the Ksp, the more soluble something is. So if you have a Ksp and it's going to be like, let's say it's like 1.0 e to the minus 3 versus 1.4 e to the minus 9. Let's say that these are the Ksp values. They'll write it like Ksp equals. The one that has the 1 e to the minus 3 is more soluble, which means that more of it can dissolve in water. Okay, now, anyway, the smaller the number, the less soluble something is, the less that you could dissolve in a given amount of water. All right, so anyway, let's do this one here. It says, write the Ksp expression for magnesium fluoride. So the first thing, this is just like any other equilibrium expression, except you first have to write the dissolution equation, or sometimes we call them the dissociation equation. So you would have to look up the charges, mg plus 2, this is minus 1. So it's mgF2. So we're saying that this is a solid. This is how all Ksp problems go. Okay, now when you put mgF2 in water, it's going to dissolve and it's going to break into magnesium ions, Aq, and fluoride ions, -1, Aq. Then you got to balance this little mini equation that you did here, this dissolution equation. I believe that's what AP calls it, is a dissolution equation. So you got to balance the equation, that's important. Okay, then you're going to write Ksp equals, and it's just like any other equilibrium expression. Remember, solids and pure liquids are not in the expression. So the expression is just mg 2 plus to the first power, because you use the number in front, remember, whatever number that is in front, so that's like a 1. And then f, -1, okay, to the second power. A big mistake is somebody putting like a 2 in front of the f. No, that doesn't go there. Okay, that's only, you take care of that in the ICE table. Okay, so it's just the ions in brackets and then whatever power they go to. Okay, so that's your Ksp expression for magnesium fluoride. All right, now you can do a math problem. It says, what is the Ksp for magnesium fluoride when a solution contains 2.7 e to the minus 3 molar magnesium ions and 5.4 e to the minus 3 molar F minus 1 ions. Okay, so at equilibrium. So basically what you do is you just take your expression and you plug in the numbers and do the math. So Ksp would be equal to magnesium, and that's 2.7 e to the negative 3 times 5.4 e to the minus 3, but we have to square it according to the equation up there. And so if you do the math, let's see, I believe it equals 7.9 e to the minus 8. And they don't put any units on the Ksp values. All right, now let's see here. What other thing? Oh, significant digits. Because each of these has 2 significant digits, you should report your answer to 2 significant digits. All right, let's keep moving on. All right, now here's another problem right here. It says, what is the molar solubility of lead chloride? Okay, and actually, I didn't type this right. It should have been lead Roman numeral 2 chloride, so make that change on your worksheet. All right, so the first thing is you want to write the dissolution equation. So we got PbCl2 solid, and that's going to break, when you put it in water, it's going to break into lead ions, 2 positive, Aq, plus chloride ions, Cl -1, Aq, and then you put a 2 in front to balance your equation. All right? So now what we're going to need to do is we're going to need to write the expression. So the Ksp expression is going to equal lead 2 plus times chloride -1 to the second power. Okay, remember solids are not part of it. Okay, next step is we're going to make an ice table. So normally with equilibrium problems you're going to make an ice table. So initial concentration, oops, that's supposed to be equilibrium. All right, now the thing is solids are not part of it, so you can just put a thing there. So before you put this in water, or the instant that you put it in, there's 0 and 0 because nothing's dissolved yet. Now this one's going to go up by x, so plus x, so 0 plus x, so at equilibrium we're going to have x. The chloride ion, however, is going to go up by 2x. See, there's the 2 there. So at equilibrium we're going to have 2x because 0 plus 2x is 2x. Now we just plug everything into our Ksp expression. So Ksp is going to equal x to the first power because there's just one lead. And the chloride is 2x, and that's going to go up to the second power. All right, so then now we can plug in this Ksp value, which I should have done anyway before that. So I should have put the number in there instead of the Ksp. But anyway, let me just erase this and put the number in. All right, so anyway, the number is 1.17 e to the -5. That's the Ksp. All right, now we can solve it. So we get 1.17 e to the -5 is going to equal x times 2x squared. Well, you got to square the 2 and you got to square the x. So that's going to make 4x squared. So we're going to have x times 4x squared. And one of the big mistakes sometimes is forgetting to square the number. Okay, so that's 4. 2 squared is 4. So that's 4x squared. And so if you multiply that, you get 1.17 e to the -5 is equal to 4x cubed. Remember, you add exponents. Okay, so you're going to divide both numbers by 4. And then what you're going to do is take the cube root of that. And so I end up getting x is equal to 0.0143. Now I went out 3 significant digits because the Ksp is given to 3 significant digits. Now, how do you take the cube root of something? So if you're doing the math here, which I kind of skipped ahead a little bit, I just had it written down on paper. So anyway, but if you take 1.17 e to the -5 divided by 4, you end up getting this number. You get 2.925, something like that. Oops, don't want that. Want my pen back. E to the -5, or -6. Okay, now to take the cube root of that, I just take this number, this 2.925. So on my calculator, I take 2.925 to the power of 1/3. So if you do the inverse of the whatever number this is, that's how you take like a cube root. And that's how I ended up getting 0.0143. Okay, why don't you pause the video and try to see if you can do this problem right here. What is the molar solubility of saturated silver 1 acetate? Okay, so you're going to start off with silver +1, acetate is C2H3O2 -1, and that's a solid. You'll have to write the dissociation or dissolution equation and then see if you can do it. So pause the video here and see if you can do it. Then I'll show you how I work through it. Okay, so anyway, to finish this equation, you would go Ag, and that's going to be Aq. It's going to break into silver ions, plus C2H3O2 -Aq. All right, and so then you can write the Ksp expression. So the Ksp is going to equal Ag and acetate, C2H3O2, -1. All right, that's the Ksp expression. We make our ice table as the next step. And so we got initial, change, equilibrium. So solids don't matter, remember, in equilibrium expressions. Okay, so this is going to go up by x. This one's going to go up by x. So at equilibrium, you're going to have x and x. So then we can plug in our numbers. So 1.94 e to the -3 is equal to x times x is equal to x squared. So take the square root of both sides. X is going to equal 0.044, and because this has 1, 2, 3 significant digits, I need to put one more, and so that would be a 0 there. Okay, now I guess that should be, the units would be molarity when it says molar solubility. Okay, now what, I didn't really explain this too well before, but the molar solubility is like if you're trying to dissolve lead to chloride, okay, the maximum amount that the maximum concentration that you could make before something doesn't dissolve is 0.0143 molar. If you add more lead to chloride, it's not going to dissolve. It's just going to sink to the bottom. Okay? This is like the maximum molarity you could make a solution of lead to chloride. And I think these are all at, like, we're assuming these are all at 25 degrees Celsius. Okay, this is the maximum concentration you could make silver 1 acetate before it won't dissolve anymore. That's what molar solubility is. All right. Okay, here's another problem. You could try to do this one yourself if you want to pause the video, or you could and see if you can do it. It's kind of working backwards. All right, so what is the molar solubility of MgF2? So the first thing you'd probably want to do is to write the dissolution equation. So we've got MgF2, and so that's a solid. When you put it in water, it's going to break into magnesium ions plus fluoride ions. And then we got to balance the equation. So then our Ksp expression would be magnesium times the fluoride to the second power. Okay, we make an ice table. All right. And solids don't count. We know that this is 0 and this is 0. This one's going to go up by x. This one's going to go up by 2x. Okay, but now here's the thing. At equilibrium, we know that this is x. And x is the molar solubility. And they're telling us what that number is. So we know that x equals 2.7 e to the -3. And if we know what x equals, then we automatically can just take 2 times x to get what the fluoride is, which is 5.4 if you take 2 times x, and that's e to the -3. Because the x is the molar solubility. So when we know that, and then we can get those numbers, then we can just plug them into our expression to get the Ksp. So 2.7 e to the -3. And then we're going to take 5.4 e to the -3. We're going to square that. And so we get the Ksp equals around 7.9 e to the -8. Okay, here's 2 problems that I'd like you to try on your own. See if you can do it. Then you can come back to the video and see if you get the right answer. So pause the video, try these. All right. So first thing, write the dissolution equation. Mg3ASO4 2. Okay, that's going to be Mg plus 2 plus ASO4, and that's going to be -3. Okay, now these are AQ. Balance our little equation. We got to have a 3 there and a 2 there. All right, so then we'll write the Ksp expression. So Ksp is going to equal magnesium to the third power, AsO4 to the second power. Remember, I'm using the numbers in front for the powers. Okay, now we'll make our ice table. I forgot to write that this was a solid. All right, now solids don't matter. So we got 0, 0 initially. Change equilibrium. Okay, so this one's going to go up by 3x because there's a 3 there. This one's going to go up by 2x. So at equilibrium, we're going to have 3x and 2x. Now we just plug them into our expression with the Ksp. So we got the Ksp is 2.0 e to the minus 20 is going to equal 3x cubed times 2x squared. Now, when you do this, you got to be careful because a lot of people, I don't really know why, but instead of doing 3 cubed, they go 3 times 3 and they get 9. But it's 3 cubed, so you got 2e to the minus 20 is going to equal 27, because that's 3 times 3 times 3, x to the third power, and 2 squared, so that's going to be times 4x squared. So then you get 2e to the minus 20 is going to equal, let's see, 27 times 4 is 108. X, remember you add the exponents, x to the fifth power. Okay, divide both sides by 108 and take the fifth root of it, and you get x equals 4.5 e, that's 4.5 e to the negative 5. That's what x is. Okay, so that's the molar solubility of magnesium arsenate. Okay, 4 points supposed to be 4.5 e to the minus 5. Notice I kept 2 significant digits because that's what they give you with the Ksp. Okay, now the last part is calculate the concentration of each ion in solution. Well, now we know what x is, so to do the magnesium ion, that's going to be equal 3 times whatever x is, 4.5 e to the minus 5. And then if you do that math, it's 1.4 e to the minus 4. And if you do the AsO4, the arsenate, minus 3, and you take 2 times x, 4.5 e to the minus 5, that's going to equal 9 e to the minus 5. Okay, so these are the concentrations. Those have units of molarity. Actually, I should have put molarity up here. Okay, so those would be the concentration. Okay, that's it. You should complete the worksheet that I have, or should have completed it with these notes. And that's it on basic Ksp.